So in this video we're going to talk about free body diagrams, and then we're going to go through several examples that show you exactly how to draw a free body diagram for objects in several scenarios. So first off, a free body diagram is a diagram that represents all of the forces or all force vectors acting on a single object or a single system. So most of the time it's a single object. Okay. So how do we draw a free body diagram? Well, first thing is we need to draw something that represents the object itself. Okay. So there are two cases. If you're just starting out in a physics class, you're going to represent everything as a particle. Okay, so this means there's going to be no rotations. You're not going to worry about anything like that. There's going to be no torques. So if you don't know what a torque is, that's fine. You'll worry about that later. And we're just going to draw everything as a point particle. Okay. Later on in physics or in a mechanics class, you would be looking at rigid bodies, and you would sketch the object. So sketch a rough outline of the object. Okay, so why would you do this? Well, if you're just having a box, for example, and there's a horizontal force, this box is going to move to the right, okay? And so it's not going to rotate or do anything fancy. And so we can just represent this box as a particle with a force applied to the right. So this would be a particle representation. But later on, when you get to worrying about rotations, if we have some beam and we apply a force on the left side, that's going to make it want to rotate counterclockwise. If we then take that same beam and that same force and move it to the right, this is going to make it rotate clockwise. So in this case, where you put the force matters. And so you can't just represent the beam as a particle, because you need to draw the object itself to represent where the forces are. Okay? So depending on where you're at in your physics or mechanics class, or depending on the scenario that you're looking at, you'll either draw your object as a particle or as a rigid body and actually sketch it out. The next thing that you want to do in your free body diagram is draw all force vectors as arrows. Okay, so vectors are represented as arrows, and so we want to draw all of those. And when we do that, we want to label them. So label your forces, and we're going to identify which forces have X and Y components. So some forces may be all horizontal or all vertical, but some may have both X and Y components. Okay? And one important thing is we don't want to include forces that are exerted by our object. Okay, so we are only drawing forces that are acting on our object. Okay, so just to illustrate this first point, we have an XY axis, and maybe we have a tension force that's at some angle above the x-axis. Well, now this force is going to have an X component and a Y component. Okay, and so we may even consider redrawing this in a new free body diagram. This is something I like to do with all of our force components along their respective axes. That way, when we go to do Newton's laws and sum up our forces, we can see everything that's vertical and everything that's horizontal. So, as a third step, you may want to redraw, once you've identified the components, redraw your free body diagram with only forces along x, y axes. So this is up to you. I find it declutters a little bit, especially when you have a lot of forces. And then a final step 4, if it calls for it, if the situation calls for it, you want to draw separate free body diagrams for any other objects. Okay? So in the free body diagram, you only include forces acting on your object. Okay, so if your object is applying a force to another object, you would not include that force. You would have to draw a separate free body diagram for that second object, and that force exerted on that object would be included in that free body diagram. So why do we draw free body diagrams? I'll give you an example. If we have a box and it is on a rough surface, meaning there's friction, and then say there is a tension force pulling on this object at some angle theta above horizontal. If I draw a free body diagram of all the forces, first of all, this object has a weight. Okay, that weight is straight down. There's also a normal force preventing it from going through the surface. There's our tension force that is up and to the right, some angle theta. And since it's going to be moving to the right and it's on a rough surface, there's going to be friction that is to the left. So if it's moving, let's call that kinetic friction. Okay. Then if I break this down, okay, I like to draw all of my forces and their components along each axis. So if I break this, all the forces into their components, in the positive y direction, I have a normal force plus the y component of tension. I then have an x component of tension in the positive x direction. I have the weight that is acting straight down, and I have the force of kinetic friction in the negative x direction. Okay, so now I'm ready to do Newton's laws. So if I go to sum up the forces in the x direction, now I can just come over here and find all of the horizontal forces. So this just tells me that I have a positive x component of tension and friction is in the minus x direction. So I get that from here. Then maybe I want to sum the forces in the y direction. Well, I come over here and I have positive normal force and y component of tension in the positive y direction, and then my weight is going down. Okay, so this made it super easy to look at my free body diagram and see which forces are in which direction. And if you notice, if you have a good picture, whether it's given or you can draw it from the problem, your picture turns into a free body diagram. And then you can simplify your free body diagram into forces along each axis. And then from there, when you're ready to actually do math and use Newton's laws to solve your problem, your forces are just filled in automatically from your free body diagram. So this makes it much easier than just reading a problem and trying to fill in Newton's laws or sum up all of your forces if you didn't draw them out. So now let's look at an example. So we have a man holding a box at rest versus the box at rest on a table. So I'm going to draw a table. Sometimes it's good to have a picture before you start drawing your free body diagram. Forgive my picture. So this man is holding a box. And then down here we're going to have that same box, but it's going to be resting on a table. Okay. So our free body diagram in this case, the box is going to have a weight that is down, but the man is applying a force up to keep the box from falling. So we'll call this force from the man's hand, and it's going to be up. Down here we have the weight of the box again going down, but now it is the normal force of the table that is pushing the box up. Okay, so notice the weight was down in both cases because it is a force from gravity. It's often easy to get your normal force and weight confused for action-reaction pairs, but in this case they are not. Okay, action-reaction pairs. Okay, the weight is a force from on the box due to gravity, while the normal force is a force due to the table. And also action-reaction pairs shouldn't show up in the same free body diagram. Okay, so let's look at another example where we have a slope. So we have a skier that is sliding down a frictionless slope. So I drew a kind of a steep slope. So we have a skier having a good time going down the slopes. We're going to draw a new rotated set of coordinate axes. So I'm going to put my positive x direction going down the ramp and the positive y going perpendicular to the surface. Okay. And so one reason why we want to do this is because it makes it where more of our forces are aligned with our coordinate axes. Okay. And that makes finding the components of our forces a lot easier. So now our normal force is going to be perpendicular to the surface, but it is now aligned with our new y-axis. Okay. Then our weight is always straight down. Okay. So draw my coordinate axes, x, y. And one thing to note is this angle is always going to be the angle of the ramp, the angle that your weight makes with your new y-axis. And so I think it's worth seeing why that is. You have your y-axis and your x-axis, and in this case we rotated it to the left. It's kind of bad. Let's see if I can get this. So in this case we rotated to the left by some angle theta. So that means this is also theta, this is theta. Okay, actually this should be my positive x-axis. Okay, and this is theta. So we rotated our entire coordinate system by the same angle. And so since our weight used to align with our y-axis, our positive y-axis, and we rotated it an angle theta, now our weight is going to be this angle theta with respect to our new y-axis. Okay, so now our weight would have been straight down, so now it makes this angle theta. Okay, so if I wanted to draw my y component of weight and my x component of weight, I could find that using sine and cosine of this angle. Okay, so another thing that's worth pointing out is a lot of students have trouble drawing this right triangle and figuring out which way to write it. Sometimes they have their weight going down, but then they will make a triangle like this. And this is bad because, number one, notice that this component isn't along either of our axes. Okay, so this is not an x or a y component the way I've drawn my axes. So that tells you that it's wrong, number one. Number two, our vector should always be the hypotenuse. But here it's drawn as a leg. Okay, and so that should give away that this is incorrect. If you draw it correctly, your weight or your force vector should be the hypotenuse. And then not only that, but your x and y components should make right angles because the x and y axes are always at 90 degrees to each other. Okay, so this tells you that you did it correctly and you drew your right triangle correctly. Okay, in the next example, we have a box pulled up a rough ramp by a rope. So I'm going to draw my ramp in the other direction so we get used to seeing it the other way. Okay, so I'm going to draw some dashes to indicate this is a rough ramp. There's going to be friction. So there's a box and it is being pulled up by a rope, so that's a tension force. So again, I'm going to rotate my axes. So I'm going to go ahead and put my coordinate system. It's a good idea to put it down first. Okay. This is my y direction. I'm going to put positive x up the ramp. Okay, you're free to change that. But the box is most likely going to move up the ramp, and so I want my motion to be in the positive x direction. I'm free to choose that. So my weight is going to be straight down, as always. The normal force always perpendicular to the surface. And since I'm pulling up the ramp with this tension force, the box is going to move up, so that means my friction force is going to be down the ramp. And again, this is my angle theta. Next example, we have a box pulled across a rough floor. So I'll draw a box and a rough floor. It's pulled by a 10 Newton force from the left. Okay, so 10 Newton force, call that T1, and a 20 Newton force from the right. So we'll call this T2 equals 20 newtons. If I draw my free body diagram, it has a weight that is straight down, a normal force that is perpendicular to the surface or straight up, and then I'm going to draw T1 to the left, and I'm going to draw T2 a bit bigger to the right. And this is going to tell me that T2 is bigger than T1. And then because it's a rough floor, it's going to have friction. So I need to figure out which direction it's going to move. Well, since T2 is bigger than T1, it's likely going to accelerate to the right. If it accelerates to the right, that means friction is going to be acting to the left. Okay, so some people draw a separate arrow. If they have two forces in the same direction, I like to just put T1 plus friction, or my forces added together. To me, that helps keep it from getting cluttered. There are cases where you may have three forces in the same direction, and that is really hard to see if you draw three arrows right side by side. In the next example, we have two blocks stacked on top of each other, and the top block is attached to a wall by a rope from the left, and the bottom block is pulled to the right across the rough floor. So we have, this is my wall, and this is my rough floor, and call these blocks A and B. Block B is attached to the wall, and block A is being pulled to the right. Okay, so I need a free body diagram for block A. Okay, so if I draw that, I have the weight of block A. I also have a force from block B that's pushing it down, so I'm going to call this force from B on A. Okay, so other people may use a different notation, but I'll call this force of B on A. And then there's a normal force from the floor acting on A, so normal force of A. There is a tension on A, pulling it to the right. And then this tension is going to make it where object A tends to move to the right. So that means it's going to cause friction to the left. So there's going to be some kinetic friction with the floor. Okay, but not only that, so if we just draw the bottom of box A, it's going to accelerate to the right because of this tension. And so friction is going to push it to the left. But then if we draw box B, again, this surface, the top surface of A is going to be going to the right across, sliding across B. So that means that there's going to be some friction to the left from block B. So we're going to draw friction, kinetic friction from B. Okay, so now we have two frictions. Okay, so there's 6 forces, so quite a bit going on. If we then draw a free body diagram for block B, okay, it just has a weight going down. Okay, nothing on top of it pushing it down. It has a normal force on it, this time from block A. So this is going to be, we could call this the force of A on B. Okay, so this is not a separate force, this is the normal force. And then B is being pulled to the left. Okay, not only that, since there's friction on A due to B to the left, there must be friction on block B to the right due to A. Okay, and so really quick, I want to notice these are action-reaction pairs. They're in opposite directions. They're equal in magnitude. And one of them is from A acting on B, and one of them is from B acting on A. So it's by 2 separate objects. Not only that, block A is exerting a normal force on B. Okay, so either of these. And block B is exerting a force on A. So all of these are action-reaction pairs. Okay, so notice the pairs of forces occur in different free body diagrams. You never have both forces in the pair occurring in the same free body diagram or on the same object. One of the forces is from the first object acting on the second, and the reaction is the force from the second object acting on the first object. Okay, and these should be equal and opposite. And when we identify interactions between an object, so when we saw that there was a force of friction on B from A, or on A from B, and then this normal force, or this force from B on A, we knew that these forces had to exist. Okay, they had to show up, and they had to be in the opposite directions as they were in our free body diagram for A. Okay, so that's helpful in identifying all of your forces and not forgetting any, but also in identifying action-reaction pairs. Okay, in our next problem, we have a block A that is pulled up a rough ramp by block B, which is connected by a rope over a pulley. So I'm going to draw roughly what this has in mind. So you have this rough ramp and a block A. There's a pulley where block A is being pulled up by this block B. This is on the other side. Okay, so block A is being pulled up, so block B must be being pulled down. Okay, so I'm going to start with the free body diagram for block A. And I'm going to draw my rotated coordinate system. I'm going to draw the positive X direction going up the ramp, positive Y perpendicular to the ramp. So this block has a weight that is straight down. It has a normal force that is perpendicular to the surface. Then the tension in this rope is going to pull it up the ramp. And since it's going to be pulled up the ramp, friction is going to fight it and move down the ramp. Okay, and this is our angle theta that the ramp makes with the horizontal. Okay, now I'm going to move on to block B. And one thing that is useful to keep in mind, these coordinate systems, again, are just a tool that we use to identify our forces and their directions. We can have different coordinate systems for each object. Okay, so for block B, I'm going to have a normal horizontal and vertical coordinate system, and it's going to have a tension force that's in the positive y direction, or straight up, and the weight of block B is going to be straight down. Okay. In this case, I'll do something else that might be unusual. I'm going to put positive y direction in as down, straight down, because block A is going to move up the ramp. That's in my positive x direction. And so I'm going to have, since block B is going to be moving down, I'm going to call that positive y. And that's perfectly okay. So this is okay to have different coordinate systems. Okay. And in this case, if our block accelerates up the ramp, so block A accelerates in the x direction, this is going to equal the acceleration of block B in its y direction. Okay? And so this would be useful in solving problems, and this is how you could go back and forth between coordinate systems. This block A is only moving in x in its coordinate system, and block B is only moving in y in its coordinate system. So this is perfectly okay to do. Okay, we have another problem where 3 blocks are hung from an O-ring by a system of ropes. So forgive my poor drawing. And we're going to draw a free body diagram for the O-ring for blocks A, B, and C. Okay, so I'm going to start with the O-ring. The O-ring, it's going to have a weight that is straight down. So first, I like to consider all non-contact forces. So in that case, it's the weight, or the force of gravity. And then we're going to look at all the forces that are actually touching the O-ring. So in this case, there is a tension that is downward toward A. So I'm going to label these cables, or these ropes, 1, 2, 3, 4, and 5. So in this case, the tension in C, or 3, not C, is pulling on the O-ring downward. And then the tension in ropes 1 and 2 are also pulling away from the O-ring. So the first one is pulling T2 at an angle theta 2 from horizontal. And then T1 is pulling at a different angle, but again it is with respect to horizontal. That's T1. Okay, and so that is our free body diagram for the O-ring. Okay, we looked at the non-contact forces, and then we only looked at forces that were in contact. So once we got the weight, we only considered forces that were in contact. And so since blocks A, B, and C are not touching the O-ring, they shouldn't show up in our free body diagram. Okay. Then if we look at block A, well, I'm going to draw block A by itself to do just what I said. I only want to consider contact forces that are touching A along with its weight. So if I draw the free body diagram, I know that block A is going to have a weight. But then once I get all the non-contact forces, I only need to look at the forces that are directly touching A. And in that case, there are 3 tensions. There is tension 4 and tension 5 that are pulling down. And then there's tension 3 that is pulling up. Okay? And then if we look at blocks B and C, they're going to look very similar, so we'll do them together. Block B has its weight going down, and then aside from its weight, it only has one other force making contact with it, and that is the tension in rope 4. It's pulling up. And likewise for block C, we have the weight of C pulling down, and then the tension in rope 5 pulling up. And keep in mind, tension always pulls away. So tension never pushes. So it will always be drawn going away from the object. Okay, let's look at another problem that involves a spring. So we have a block that is connected to a spring that is stretched up a rough ramp. Okay, so this is kind of a weird problem, but we've seen stuff like this. Okay, so this ramp makes a certain angle, and you have a block on a spring. Okay, so maybe I'll do my block in a different color. Okay, and it's really important to notice that it says it is stretched up the ramp, so it's not our spring being compressed down, but it is stretched up. So if we draw a free body diagram, again, we're going to have rotated coordinates. So I'm going to make my y perpendicular to the surface, and my x component is going to be along the surface. So you can pick whichever direction you want for positive x. My block is going to have a weight that is straight down, makes the same angle theta as the ramp does with the horizontal. The block will have a normal force that is perpendicular to the surface. And then the spring force, since it's being stretched, it's going to try and restore itself to equilibrium or pull the block down. So this is F spring. And since it's going to pull the block down, that means friction is going to fight that motion and act up the ramp. Okay, another problem, we have a book that is pushed upward against a wall as it slides down. Okay, so we have things going a little bit different direction. So we have some force applied upward at an upward angle. Okay, so if we were to draw the free body diagram, we would have the weight of the book acting down as always. This time the surface is vertical and it's keeping the book from going to the left, so the normal force is to the right. We have our applied force that's pushing up and to the left at this angle. It's not 20, it's just some angle theta. So I'll just call this F push. And then since it's sliding down across the wall, then we'll have friction that fights that motion and points parallel to that motion, or up the wall. So in this problem, we have a man standing on a scale inside of an elevator. So this is sort of a classic problem. So we have an elevator, and then we have a man inside, and then that man is standing on a scale. So we're going to do the free body diagram for the elevator, the man, and the scale. So the elevator, it has a weight itself, and then it's going to be pulled up by some tension in some big strong cable. Okay? And then this scale is pushing down on the elevator as the elevator pushes up on it. So there's going to be a normal force from the scale on the elevator. Okay? So now we can look at the man. The man has a weight, so the weight of the man downward. And then the scale is going to exert a normal force on the man to keep him from going through it. So normal force from the scale on the man. Okay, and then if we look at the scale has a normal force from the elevator on the scale. So the elevator is pushing up on the scale. And then the scale itself has a weight. And then there's a normal force from the man standing on the scale. So for the man on the scale, okay? So I want you to recognize action-reaction pairs of the normal force of the scale acting on the elevator, so force down, and there's an equal and opposite force up for the normal force of the elevator pushing on the scale. So that is one action-reaction pair. And then we have another, the normal force of the scale on the man and the normal force of the man on the scale. Try to draw it like this. Okay. So these are action-reaction pairs. They occur in different free body diagrams. They're both between pairs of objects, but only one object exerts one of the forces and the other has the force exerted on them. Okay, so these are our action-reaction pairs, and you may be asked to identify them, or it helps to make sure you don't leave out any forces. In the final example, we have a rock twirled in a horizontal circle by a string. So we have a string attached to a rope, and it is being twirled in a horizontal circle. So at each point it is moving tangential to the circle. Okay. And if you look top down, so I like to get top down views, especially when things go in circles. It's very useful. At this point, the rock has a tension force toward the center that's keeping it going in a circle. Okay. So if we look at a side view, this is where it's useful to draw our free body diagram, X and Y. We have a tension that's pulling this force kind of up and in, but from the side, if we were to look at this from the side, this is my little eyeball, then the tension force is going to be up and along this rope or this string, and then the weight of the rock is going to be straight down. Okay, so some might ask a question, why isn't it just drawn horizontally? So why isn't your free body diagram tension straight to the right and the weight straight down? Well, it says that it is spun in a horizontal circle. Well, if it's in a horizontal circle, that means it's not accelerating up or down. And if you had this, there's only one force in the y direction, and that's the weight. And so if there's only one force in the y direction, that means that the rock would accelerate downward. Eventually you would hit the ground and it would stop. So if you want to keep it going in a horizontal circle, you have to apply some upward component in your tension, so the upward component, to keep the rock from falling. So to keep the rock at the same height. Okay, so this is just a little bit of analysis. If you look at this, the tension is keeping it going in a circle, but you need some component of the tension that's up to cancel out this y component of the weight. Otherwise, your rock is just going to accelerate downwards as it's going in a circle. And so if you ever actually go outside and twirl a rock, no matter how fast you twirl it, you will notice that you can't make this angle smaller than some minimum amount. Okay, and it's because you always have to have a force going up to keep your rock from falling. Okay, so this is a little bit of analysis that goes into thinking about your forces before you make your free body diagram.